Welcome, everybody. It's my pleasure today to introduce Uzu Lim, who will be telling us about strange random topology of the circle.
Hi. So I'm a PhD student in Oxford, and today I'm going to talk about some strange random topology of a circle. Slightly generalized title, but there is a specific message that I want to sort of circulate in the TDA community through this specific investigation I've done. So it all starts with this general problem of topological inference. So a very general setting goes like this. You have a manifold M. It can be embedded in Euclidean space or not, whatever you choose. And let's say Xn is independently identically distributed sample drawn from your manifold M. And then one of the key tenets, and it's a vague one, is that the virtuous ribs, VR, and Czech complex drawn from, constructed from Xn recovers the topology of M. There's a lot of result done in this recovering topology tenet. For example, starting from Hausmann's big paper in 1995, and there's another big paper by Niogi, Smale, and Weinberger, 2008, and some more recent works have been led by Omer Boborovsky. So there's a paper in 2019, Boborovsky and Oliveira, also Matt Kale, and many others. So this sort of recovering topology from your manifold is true if your filtration radius that you choose to construct your simplicial complex gets shrunk down as your point size gets larger, and usually it's at this rate. So it's n to the power of -1/d. It gets shrunken down, slowly, but certainly towards 0. And my question is, what if R isn't shrunk down? Because in practice, you can go all the way through and see what happens. And I want to initiate some more systematic investigations into these phenomena. So here's a very interesting thing that you can find from Circle. And this is not exactly what I'm going to talk about today because it's virtuous ribs complex. So suppose you have a circle, S1. So it's S1 here. And you drew, I think it was 100 points in this computational experiment I've done before. And you draw 100 points at random, and then you do the virtuous ribs construction and increasing the radius slowly 1 by 1. And then you observe how the Betti number, Betti 1 to Betti 4, change. And the conventional practice of topological data analysis states that you should be looking for persistent signal. In this case, the persistent signal corresponds to this long orange line. So you might notice this gray smudge here. The smudges are error bars from me taking iterations over many iterations of the 100-point sample. So you have a gray bar for error. But the point is that this orange plateau is supposed to be the persistent signal, and it's just 1 exactly. And the x-axis here is the filtration radius used to construct your virtuous ribs complex. But you see that at the larger radius, you start seeing 2-dimensional signal, 3-dimensional signal, and 4-dimensional signal, and higher dimensional signals I haven't plotted here, but they should be appearing actually. And you can ask, what is going on? This is quite strange. Why do you see 2-dimensional topology in virtuous ribs constructed from a circle? And one simplistic answer to this is that it's just topological quote-unquote noise, but you can actually see a very systematic behavior going on here where just 1 and then it just phase transitions into 2, and then phase transitions into 3 and 4 and so on. And in fact, you can do the same thing with a 2-dimensional sphere, and then you see a persistent signal for 2-dimensional sphere here. That's the cyan line. But the 1-dimensional signal looks funny. There's a lot of Betti number going on here, and 3-dimensional, 4-dimensional signals happen again as well. And now, if you continue increasing the dimension of the sphere, so this is for 8-dimensional sphere and is for Betti 1 to Betti 4, and the wisdom is that you're not supposed to use 1 to 4 because they're not genuine, supposedly. But you can start to see they look like Gaussian curves. This is not a proven assertion. It is a simple observation that I have failed to prove at the time, still haven't proven it. But one thing that happens when you do this thing is that as the sphere dimension increases, these Betti curves slowly drift to the right. So you might know that higher dimensional homology is hard to compute on your computer because it takes a long time. But it turns out that you can use these lower dimensional signals to actually detect higher dimensional topology as well. So a lot of funny things going on here. And the point here is to not focus solely on recovering the topology of the manifold, but instead to look at all of the radii and look at all of the lower dimensional signals as well and see what we can recover out of it. So this was one of my earlier projects, and you can actually reliably recover. You can train a machine learning classifier in order to actually learn the sphere dimension. So it is a learnable signal. But this isn't actually the topic of today's talk. I talked about Betti-Rips complex because it is one of the more computationally efficient way to do things. And today I'm going to talk about random Czech complex instead. And if you construct Czech complex for, I'm going to talk about Czech complex for a circle. And in practice, circles usually arise as embedded in two-dimensional space. And when you construct Czech complex there, nerve lemma applies because it's embedded in Euclidean space. And then, it's supposed to just give you topology of the union of balls, which cannot have higher dimensional signal. So in some sense, it's a proof of concept that's going to happen today. But what I want to continue pursuing in the future is that these investigations continue into Betti-Rips complex directions as well, because that's more commonly used in practice as far as I know. So I'll be using Czech complex that's constructed using arcs, i.e. using the intrinsic topology of the circle. So that's the topic today. We'll see some interesting, very specific behavior. So let me explain the setup. You start with Xn, your IID sample drawn from S1 of size n. So you have endpoints independently, uniformly drawn from your circle. And let's C and R denote Czech complex constructed from Xn and radius R. And again, I emphasize that it's constructed using arcs, so that is a nerve complex of arcs instead of balls embedded in two-dimensional space or something. And let's define these notations. Chi bar NR equals expected value of the Euler characteristic of your Czech complex, and B bar K NR is your expected value of Betti number, kth Betti number of your Czech complex. So we're going to study these two numbers today partly, but also study homotopy types more in general. So here's one of the big pictures that I want to emphasize to you. So if you compute the expected Euler characteristic, and the formula I'll show you in a precise, one of the main results I'll be discussing is the exact formula. So if you compute the expected Euler characteristic and then normalize it by point count, then as the filtration radius is ranging from 0 to half, where in our case, circle has circumference of 1. So at radius half, it'll cover everything and everything will be a point. When you divide it by like this and you see these strange spikes happening, as the yellow curves here correspond to larger n, and you see that they converge into these shapes. And so what's going on? One thing you should be noting now is that it is divided by n, so that when you scale it back up by multiplying by n, then these spikes will shoot to infinity. So you have unboundedly large expected Euler characteristic at these specific narrowing spikes at specific places. And these spikes locations can be computed exactly. And I've marked them by red dots here. And the kth peak is exactly, the x coordinate is this, and y coordinate is this funny number, which is this elementary function-ish. So one thing to note here is that this number is half of 1 minus 1 over k. So it's kind of just half, third, fourth, fifth, and so on. So that's how where the spikes are, and the height is plotted exactly as this formula. So let me just exactly introduce the main theorems. So there will be theorem A1, A2, and B and C. So A1 is expected Euler characteristic exact formula. So I've reparameterized R here, and it becomes a summation of these polynomials. And you sum up to floor of 1 over R, where R here actually is a variant of the radius, the filtration radius 1 minus R over 2 here right now. But you see that it's actually a piecewise polynomial function. And it's piecewise here because the summation changes as what the R is. So each of this curve here is a piecewise polynomial. And at each threshold marked here, it picks up an additional term for the Euler characteristic. And it turns out that these peaks are contributed exactly by the one term, the top term in the previous summation. And the second theorem is that the peaks actually correspond exactly to certain even Betti numbers. So you can pick any epsilon, and then for a radius falling into a certain interval, that the interval of like between the peaks just now, then it uniformly, the Euler characteristic is converging into the Betti number when normalized by dividing by n. So each peak is contributed pretty much solely by the even Betti numbers up to this inequality. So I'll show you theorem B and C will discuss this more precisely, but what happens here is that in this first peak, you get zero-dimensional homology where radius is very small and everything is scattered around. And in this regime, everything is just essentially circle. So the arcs are small and everything is contractible, nerve lemma applies. Everything is your happy land from what we knew before, where everything is just circle and just scattered points. Now, at the half threshold, your nerve lemma stops applying because you can have arcs that have intersection going over like this, and the intersections will be disconnected. And at that point, you get two-dimensional spheres, and it turns out it's a bouquet of two-dimensional spheres, where bouquet here refers to wedge sum of two-dimensional spheres. And then again, when it dips down again, it's three-dimensional sphere, and 4, 5, and so on. So notice at the moment that odd-dimensional spheres Euler characteristic is 0, so it really dips down to the bottom. And even-dimensional spheres Euler characteristic is positive. If you wedge it, it blows up by how many times you wedge it by itself. So A1 and A2 is about Euler characteristic and Betti number. And now it's about B. So if we specify K, epsilon, and delta, then if we say that the radius parameter is within a certain radius tau K from a midpoint mu K, then for sufficiently large n, the following holds with probability at least 1 minus delta. So it holds with arbitrarily high probability, so to speak. And the homotopy equivalence is that the Czech complex is homotopy equivalent to an odd-dimensional sphere. And the midpoint, the nu K and the tau K are given by these expressions, and looks a bit funny. The point is that they're just, so this is nu K, and this width is half of this width is the tau K. So we're talking about how odd-dimensional sphere dominates each of these regimes in 1, 3, 5, 7, and so on. Right. Actually, I'll remark, B is easy to prove. We'll see later. C is hardest to prove here. So what is it? You start with integer K again, greater or equal to 2. And then now we have radius that's within a certain moving rho Kn and less or equal to sigma K divided by n. So this time, where the radius must fall in is shrinking, smaller and smaller. But bear in mind, this isn't radius itself shrinking, so to speak. It's the interval that the radius must fall into shrinking. So for sufficiently large n, the following holds with probability at least half k omega k, and I'll explain the quantities later. And the homotopy equivalence is Czech complex is homotopy equivalent to a fold wedge of 2k minus 2-dimensional sphere, where a falls in between omega k over 4 times n, a plus 1, and then n over k. So the main point here is to notice that n appears in both of these. So that means this wedge sum, how many times this wedge becomes arbitrarily large as your point count grows large, it falls into this linear bound. But you see that these homotopy types must appear a lot. The very high dimensional topology must happen in these small intervals. And the numbers are given by this. And so I separated out the k part, and this is the location of the phase transition sort of behavior from just now, where I'm using the word phase transition differently from the typical literature on this topic. And there's a movement along n. And this is sigma k, is a pretty small number actually that controls this radius. And omega k is actually the height of the peak from just now. So it holds with probability, and this doesn't go to 1, but it's showing that it happens at least with a certain positive probability that can be computed exactly. So that's theorems A1, A2, B, and C. And that's more or less the main thing I wanted to talk about. And the rest of the time, I'll talk about some proof technique. And it's quite interesting because it's, in some sense, quite easy to work out. And so the whole business turned out to be benefiting heavily from Euler characteristic, because expected Euler characteristic is quite easy to compute as compared to things like expected Betti numbers. So the way that I obtained theorem A2, which controlled the gap between the Betti number and the Euler characteristic, is via seeing that so expected Betti number itself is quite hard to compute, but you can compute the Euler characteristic and then use it to compute the approximate Betti numbers. And the reason why expected Euler characteristic is easy to compute is because it's given by alternating sum of simplex number of simplex counts. So I'll be giving how the computation proceeds. This goes in kind of reverse to how the reasoning goes. So you start with this QKR, which is the probability of n random. Oops, it should be QNR actually. Yeah, so this should be QNR anyway. It's a probability of n random arcs of length r covering the circle. So you have randomly spaced arcs covering the circle, and it's given by this formula. This was not proven by me. It was a result from 1939, so it's an ancient result, but it somehow got dug up to be used here again. So for expected simplex count in Czech complex, what you're doing is you're looking for, so when you have n arcs and you're trying to look for k simplices, that means you're looking for all of the k subsets of n for which the arcs intersect non-trivially. And when you take the expectation value, then all of the parts from n choose k separates into separate pieces. So you're just doing n choose k, and what you're doing is probability that k arcs intersect non-trivially. And by De Morgan's law, it actually just means these arcs intersect non-trivially if and only if their complement arcs don't cover the circle. Or cover the circle is one of the two other ways, but the point is that it can be reduced back to Q. And that's what exactly this is. So you can do simplex count this way. And finally, for Euler characteristic, you have this expected value, breaks down into alternating sum of simplex counts, and you plug in the formula from just now, do a bit of algebra, just a few lines, then you get this sum. yeah, it's a sum. So r prime here is 1 over 1 minus r over 2. And as I mentioned earlier, the floor of 1 over r term dominates, and it produces each spike. So second proof ingredient comes from homotopy type constraints, and this one heavily owes to the paper called Nerve Complex of Circular Arcs, where all of the homotopy types of nerve complexes from circular arcs distributed on a circle, and it doesn't even need to be arcs of same length. They have been classified completely. And it turns out that they're either odd dimensional sphere or bouquet of even dimensional spheres. So the nk here is for n evenly spaced points, and it's for, you have k jumps to construct maximal simplices, and you have a nerve complex. So it's the same as Czech complex for n evenly spaced points. And there's exact classification like this, where conditions are about how the fraction k over n falls into a threshold value or between the threshold values. And the reason for all the spikes appearing from just now would be attributable to us asking for k over n to be an exact threshold value. And the long stretches of even odd dimensional sphere would be corresponding to this. It's very peculiar. It's a very specific topological behavior. But due to this being very narrow possibility, using Euler characteristic, computing Euler characteristic makes things quite easy to infer information about homotopy type, because sometimes, so if the Euler characteristic was 100, then you can see that it can't really be due to the odd dimensional sphere. It has to be due to the even dimensional spheres. Yeah, the bouquet of them. And turns out that the set of all a comma b such that your Czech complex, there's a missing n here, homotopy equivalent to a fold wedge of 2b sphere. So set of all a comma b, it's a subset of z times z, where z is set of integers. It belongs to j less than k union jk, where j less than k looks like a and b. Well, you have a bunch of inequalities like this, and jk, you get things like this. But the point here is actually to look at what bound for a you get. And then you can see that the a is upper bounded by this number that's predetermined by k and b is again bounded by k. So you can't have too many self wedges here. But jk, you have the a bounded above by n over k, and it can go arbitrarily large as n goes very, very large. So when the Euler characteristic spikes up, you can see that it's contributed from this jk, i.e. when b equals k minus 1, so that we're looking at 2k minus 2 dimensional spheres. So that's where all the contributions come from. So how do we use this to get to homotopy type constraints? So so only even bouquet contribute to the Euler characteristic, because for even odd dimensional sphere, you get, the Betti numbers are like, for circle is 1, 1, for 3 spheres 1, 0, 0, 1. And then when you take alternating sum, everything cancels out into 0. So you only, when you see positive Euler characteristic, that means contribution from bouquet of even dimensional spheres. So chi bar and r, you might recall the notations expected Euler characteristic, and that's a summation of a plus 1 times pa comma b, where pa comma b is probability that your Czech complex is homotopy equivalent to a fold wedge of 2b spheres. So you have the possibility that a can go from, say, like 1 to 1,000 and so on, and there are all these different probabilities contributing to the Euler characteristic. And we don't have much other information at this point, But just from the information that Euler characteristic is growing large, we can reverse infer what happens to the probabilities. So as per just now, we split the sum into less than k plus ak. And this is exactly for the two split just now, as I was talking about. One stays finite, another can grow to infinity. So since a less than k is less than k, we have that chi bar is bounded between ak and k plus ak. So that when you divide it by n and n grows into infinity, then these normalizations, they're the same approximately. And you saw earlier that Euler characteristic, when it's normalized, it converges into spikes of specific heights. And that is equal to this quantity divided by n. And a plus 1 is allowed to grow up to n over k, so that these various combination of these probabilities are contributing to the Euler characteristic growing large. And you can see that it's only 2k minus two-dimensional sphere that's contributing right now. So yeah, that's the homotopy type constraints. And the last bit is a more familiar story used to just obtain the bounds for an odd-dimensional sphere, because so you can actually use the Euler characteristic tools to work with the odd-dimensional sphere as well. But this is arguably much simpler argument. And I think that a variant of the argument I'm going to give could give a bound for the even dimensional spheres as well, but it's more tricky because you might see soon why it's tricky. So this comes from this result comes from, so this is not my result, what's stated here. It's about the Beatrice, the Czech complex of the full circle at radius r, and it's infinite, like you have all of the points on the circle to construct the Czech complex. And turns out that there is this phase transition sort of behavior again, where you get S1 and then S3 and S5 and so on according to these interval values. And that's what exactly contributes to the plateaus from the jump and plateau thing you saw earlier. And you have a minute blip of two-dimensional spheres, but it's wedged by itself to the cardinality of continuum. But then it is not a persistent signal by definition, because it happens for exactly one value of r. So if you want to apply a persistence argument here, then this will not work. You'll have to work with a finite point sample instead. So regardless, the argument here will be to work with a random sample xn and then compare it to the circle. And arcs of length r, center and xn covers S1 with probability QKR, where QKR is the probability of k arcs of, it's QNR again, that's a mistake, but n arcs of length r are covering the circle. So, when you do this, I think there might be an R/2 sort of issue lurking here somewhere, but for the sake of exposition, let's ignore it for now. But the point is that the Hausdorff distance between the random sample and your circle will be small, will be within R. And another typo here, it should be xn and S1. So we're trying to bound the Hausdorff distance between the random sample and the circle itself. So it should be xn and S1, that's a typo. And it is less than R with probability at least QKR. And when K should be n grows to infinity, this probability converges to 1. So when this happens, the persistent bars of the Czech complex for this odd-dimensional sphere, it's long and there's only one bar, and it shrinks at most by R, by persistence stability argument. And the thing about this classification of homotopy types is that when you see just one, say, three-dimensional bar, then it has to be three-dimensional sphere. It can't be anything else. So you can reverse infer the homotopy type from this persistence argument, where you are only seeing the homology group information at the time, but you can infer the homotopy group information as well here. So yeah, that's the third ingredient, and that's just used to prove the odd dimensional sphere part. And it's a much shorter argument that heavily depends on this computation of homotopy type of Czech complex. But that actually is it. That's all I want to talk about today. Thank you.
Thank you so much. So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. So we'll go first to public questions, meaning they're part of the recording, but then after that, we'll go to private questions. And yeah. So let me ask this question from Tommy first, although Tommy, do you want to unmute yourself and ask it?
Yes, I was just wondering, theorem B, yeah, which quantities depend on delta?
Oh, it's the probability.
Is that it?
Yeah. So what this theorem is saying is when you specify epsilon and delta, then I can tailor this, not tailoring, but like the n can be growing large in order to make these things happen. So it's like if I said delta is 0.01, then I can make this homotopy equivalence happen with probability 99% of probability. Does that make sense?
I see. Yeah,
So
I was expecting the probability to depend on some quantities that depend on delta, but yeah.
So if you go all the way down, there's a more precise version of the, well, it's not really on this slide. It is on the preprint, but the probability is I'm not sure if like this sort of thing is what you're looking for. So you can give a precise lower bound for the probability happening using this QK quantity. But delta is just it makes the exposition simpler when I put it like this.
Okay,
Thank
you.
Then what happens if delta goes to 0?
So it's about whenever whatever tiny delta you supply, we can find large n such that it is happening. So you can take delta as small as you want, but the smaller the delta, the larger the n you need to have in order to make the probability be at least 99.999% and so on.
Okay, so n depends on delta.
Oh, right. So I see what you mean. So it's for n sufficiently large. That's what's happening, and that depends on epsilon and delta.
Okay, thank you.
Yeah. That's good to clarify.
I have a question. This is Ira. Early in the talk, you had sigma k, and you had it 2560. That number. Where did that number 2560 come from? Did I miss something? It's interesting.
So yeah, it's how should I put it? It's just things when you start computing these bounds, numbers start going to the bottom and they start accumulating. I've experienced this before in another paper that I've done. It's not. I don't think this is not a sharp bound. It's a bound that exists, but you can produce a sharper sort of result actually. There's more wiggle room in terms of like what probability you get, and like these numbers can get even a bit larger and so on. But this is maybe for the sake of exposition is kind of the simplest expression, and then when you start collecting things to make things simplified, then you get large constant in the bottom.
Okay, thank you.
Uzu, I was wondering if you could go to theorems A1 and A2 again. I wanted to parse them. Okay, so you, in theorem A1, you fix n, I see, and then you give an exact value for the expected Euler characteristic.
Yes, expected Euler characteristic in this case can be computed exactly.
Okay. And then theorem A2 is sort of, you're giving windows on the 2K dimensional Betti number, and you're sort of saying that the 2K dimensional Betti number is approximating the normalized Euler characteristic within this, with a little bit of error. Is that right?
Mm-hmm. So let me see. Remember this, there's this expression in the last part that I just gave. So it says that Euler characteristic is approximately equal to this AK. And that's all the contribution from the 2K minus 2-dimensional spheres here. And the only way that you get contribution from the only way to get contribution into the even Betti number is via this probability of the wedge sums of spheres happening in that dimension. And so that's how that enters. That bottom line directly implies the theorem A2. So it's the sort of very narrow set of possibilities of homotopy types that make a lot of these acrobatics possible. If there were more possibilities, I think it would be much harder to obtain constraints like this. And for example, for higher dimensional spheres, much less is known, as some of the audience might know.
I'll just make a brief comment here. Maybe there's something to follow up on. I worked on this paper, Random Cyclic Dynamical Systems, with Michael Adamaszek and Francis Mata. And I think of this mostly in terms of Rips complexes, but there should be an analog for Czech complexes I'll have to think about. But essentially you sample points at random on the circle, you fix a scale R, and then you look at this dynamical system, which is each point moves as far as it can in the clockwise direction, distance at most R. And so we try to study, the number of periodic orbits and things like that. But that relates to the number of spheres in the Rips complex. So I'm curious if there's a Czech complex analog, because in that language, you get very tight results on the number of periodic orbits. And so in any case, I'm curious if there's a dynamical system that random dynamical system that really your results also give strong results about the number of periodic orbits in such a random dynamical system, potentially.
Yeah, so I remember talking about this with you. I think it'll be really good to find ways to enmesh these tools together in order to produce better results. It's worth thinking about indeed.
Further questions? All right, well, let me stop the recording here.